Oftentimes, a set is not made up of multiple sets that are mutually disjoint, and this is the reason why we have theorem 9.3.3. It's called the inclusion-exclusion rule for two sets or three sets. This could be obviously generalized for more sets, but we're going to stick to two or three sets. To kind of imagine a scenario, think about this problem kind of like over here, where you have a classroom and some people who have taken quiz 1, 2, and 3 and scored, certain numbers. Some of the same people could have scored a high score on quiz 1 and quiz 3, and some of the same people could have scored low on quiz 2. Or some people could have scored really high on quiz 1 and 2, but not so great on quiz 3. So the groups of people are going to be kind of overlapping. There's people that belong in both sets, scoring high or low. So the idea is, well, how can you separately, make the groups disjoint? You can't, but you still want to know the total. So this is the rule that we will be basically using. So let's just explain a little bit about that rule. When you're doing that problem, you want to imagine that you have a Venn diagram with two sets, set A and set B. So set A is over here, set B is over here, and you want to know the total of things inside of A and B. Now, unfortunately, if you do the A plus the B totals, you're going to be mistaken because this section got counted twice, one time for A and one time for B. So what do? Well, you just take it out once. So you calculate it once with A, for example, then you calculate it once with B, and then you just remove one of those counts and you're basically fine. That will be okay. So that's basically what the rule tells us to do. And so we're going to do that in this next problem with example number 6. So in this problem, it says how many integers from 1 to 1000 are multiples of 3 or multiples of 5. That's the key word. Okay, if you're a multiple of 3 or multiple of 5, then you could look like this. You could look like 3 and you're a multiple of 3. You could look like a 5 and you're a multiple of 5, but then you have 15. It's both a multiple of 3 and a multiple of 5. So, there's obviously some overlap. So if you try to cleanly split the sets, you're going to be double counting, obviously. So let's do that. Let's try to find the multiples of 3. So I'm going to write down multiples of 3. So I'm going to start with 3, then 6, then 9, then 12, then 15, then, 18, and so on and so forth, all the way to 999. Then that's it. There's no more, okay? I'm at the end of the list. Let's do the same thing with 5. So there's the list, and obviously, as you can see, there's some duplicates. 15 shows up in the first list and the second list. There are other choices that will show up in both lists. For example, 30, and who knows, 45, things like that. So what I'm going to do next is count the multiples of 3 and 5 at the same time. So basically multiples of 15. So this list is going to contain all the numbers that are multiples of 3 and multiples of 5. And so these are all basically the duplicates these are the numbers that showed up in the first list and the second list. Okay, so what we're going to do next is imagine that this is like the set A and this is the set B. This would be the intersection of A and B, and what we want in this problem is to calculate the total of how many elements there are in A or in B. So OR is basically like a union. So what I'm going to do is figure out the size of A, the size of B, and if I do that, then I'm going to be calculating some number twice. The 15 is going to show up twice, it's going to get counted twice. So therefore, I'm going to take away the ones I counted twice, like 50 and 30 and so on and so forth. Okay. Once I do that, then I'll be basically finished. So at this point, all we have to do is figure out what the size of the first set is, what the size of the second set is, and so on and so forth. Now to figure out the size of the set, here's what I'm going to basically picture mentally. I'm going to picture that 3 is 3 times 1, and 6 is 3 times 2, and 9 is 3 times 3. So the 3 is repeating. And the last guy in the list is 999, which is 3 times 333. So again, the 3 is repeating. So let's ignore the 3, ignore the 3, ignore the 3, ignore the 3. And how many elements are there now? Well, according to the rule from section 9.1, it's 333 minus 1 plus 1. So the size of A is going to be 333 minus 1 plus 1, which is at the end 333. So that's how many elements there are in that list, basically. Okay, so if you think about the same deal again for 5, so if you think about 5, that's 5 times 1. The 10 is going to be basically 5 times 2. The 15 is going to be 5 times 3, all the way to 995, which is 5 times 199. So how many elements are there in that list? So first of all, if I ignore the 5s, then I get a brand new list that starts with 1, ends with 199. So the size of B is going to be 199 minus 1 plus 1, which is again 199. This is again using the same trick that we learned in section 9.1. And I'm going to do the same thing again for the last one. Determine that the size is 66 elements. So now the answer is going to be the 333 plus the 199. But again, those, if added together only, they're not disjoint. They will be double counting certain elements. So that's why I got to take away the 66. Okay, so since the sets are not disjoint, I had to use the inclusion-exclusion formula. Now the final question in this problem is, what's the probability that if I chose a random integer, I'm gonna get an integer that is a multiple of 3 or a multiple of 5? Okay, and the total again is gonna be a fraction that has 466, because that's how many integers are multiples of 3 or 5, divided by the total number of integers in the list. Now the list goes from 1 to 1000, so it's got 1000 minus 1 plus 1, so basically 1000. So 0.466. Another way of saying that is to say 46.6%. So there's a 46.6% chance that if you chose a random number between 1 and 1000, your number is going to be a multiple of 3 or a multiple of 5.